Hello, good morning. I, Seema Garg, Associate Professor in Chemistry, SPC Government College, Ajmer. Today, video 129. It is for BSc Part 1, Organic Chemistry, Paper 2, Unit 2, Chemical Reactivity of Alkenes. Alkenes normally give electrophilic addition reaction. The electrophilic addition reaction in alkene involves conversion of alkene to corresponding alkanes. Here, cleavage of pi and sigma bonds occur and we will get formation of two new sigma bonds. This reaction is exothermic and alkene behave as Lewis base because of pi bond electron source. The reactivity of alkene depends upon the group attached to the alkene. If electron releasing group attached to the alkene, then electrophilic addition reactions are easier and faster. See the sequence. If it is more substituted, then reaction will be fast. The mechanism, general mechanism of the addition of the reagent, electrophile and nucleophile is a reagent. Two carbon-carbon double bond involves the following steps. In first step, electrophile attacks to the pi cloud of the alkene. See here, electrophile is attacking on the pi cloud of alkene, and this cyclic structure is occurred, and then it is decomposed to the carbonium ion. In second step, nucleophile of the reagent is attacking to the carbonium part and will get the addition product. For example, addition of hydrogen, catalytic hydrogenation. See here, when hydrogen is added in presence of catalyst, it may be nickel, platinum or palladium at room temperature, then we will get the alkane product. Sorry, here it is a alkane. It is a not alkene, it is a alkane. Addition of halogens. When alkene is treated with halogens, chlorine or bromine only, in the presence of inert solvent, carbon tetrachloride, in the absence of light, the addition of halogen occurs across the carbon-carbon double bond with the formation of vicinal dihalides. See here. The order of reactivity of halogens, fluorine are more reactive compared to chlorine, bromine than iodine. Bromination in presence of carbon tetrachloride, room temperature, it will give this dibromo product. Mechanism. Here, polarization of bromine molecule due to the pi electron of alkenes, formation of carbonium ion, then attack of bromide nucleophile, and it will give this addition product. Addition of hydrogen halides. Hydrogen halides also add to the alkenes, and we will get the product, added product. The order of reactivity of hydrogen halides is as hydrogen iodide is more reactive than hydrogen bromide, then hydrogen chloride, then hydrogen fluoride. Mechanism. First, in first step, it is polarized. It means ionized in the hydrogen halide is ionized, and then hydronium ion this is added, and H means proton ion is added to carbon-carbon double bond, and then it will give us carbonium ion intermediate. In next step, this carbonium ion will react with the halide, and it will give this addition product. The reactivity order of this carbonium ion, tertiary carbonium ion is more reactive, then secondary, then primary. The rate of the reaction depends on the stability of carbonium ion. Addition of unsymmetrical alkenes. Markovnikov's rule. Here, unsymmetrical alkenes, propene. Here, a hydrogen halide is added, may be added in two ways. If suppose hydrogen, we will get two type of product, possibility of two type, 2 halopropane and 1 halopropane. But actually, according to Markovnikov rule, we will get 2 halopropane. See the mechanism. In first step, propene is reacted with the proton. If proton is added to this secondary carbonium ion, we will get primary carbonium ion, which is less stable. If suppose this proton is added to this primary carbon, then we will get the secondary carbonium ion, which is more stable. So in this way, we are getting 2 bromopropane. Then halide is bromide is added, and we will get the 2 bromopropane. So it is called Markovnikov's addition product. See the another example. If suppose isobutene is there, then we get this product. Markovnikov's rule states that the electrophile addition to the carbon-carbon double bond involves the intermediate formation of more stable carbocation. Anti-Markovnikov's rule or addition of peroxide, or it is called peroxide effect or Kharas rule. According to this rule, here we are changing the condition of addition of HBr. Kharas observed that when unsymmetrical alkenes are treated with HBr in the presence of peroxide, the addition of HBr occurs according to anti-Markovnikov rule. See this HBr. HBr can be added in again two ways. When this reaction is occurred in peroxide, in presence of peroxide, we will get 1 bromo product, 1 bromopropane product. In absence of peroxide, we will get the 2-bromo-propane. This is called Markovnikov rule, and this is called anti-Markovnikov rule. This rule is only for HBr, not with other HCl and HF. Why? Because HCl, cleavage of HCl require 103 kilocalorie per mole energy. HBr cleavage required 87 kilocalorie per mole and HI requires 71. So when we are doing this reaction in presence of peroxide, then this alkoxy free radical has energy to cleave HBr, which is, see here, 87. It does not have that much energy that it can cleave hydrogen chloride bond. And it is also not possible with HI because it requires less energy, but reaction will be reversible. So only peroxide effect is possible with the HBr only. So alkoxy free radical will cleave HBr, and we will get this free radical, bromide free radical, and this bromide free radical will maybe attack to this primary and or maybe secondary carbon. If it is attacking to the secondary carbon, then we will get the primary free radical. If it is attacking to the primary carbon, then we will get the secondary free radical. And we know that secondary free radical is more stable compared to primary free radical. And then we will get the product. So according to anti-Markovnikov rule, peroxide effect or Kharas rule or Kharas addition of HBr, we will get the 1-bromo-propane. So it is opposite, just opposite to Markovnikov. So it is also known as anti-Markovnikov rule. Thank you very much for today's lecture.